Hi everyone, mechanics of materials. In this example, we are reviewing a structure which is consists of a boom AB, a rod BC, and they are connected. All the connections are pins, and a concentrated load of 30 kilonewton Q 30 kilonewton applied at the joint B. We want to know if we know what the boom AB area is 30 times 50 millimeters. Rod BC is 20 millimeters in diameters and has a rectangular cross section with a dimension of 40 and the thickness of diameter, which is 20 millimeters, and all the pins diameters are 25. First, we want to know what are our reactions like AX, AY, CX, CY, and then secondly, in another video, we want to calculate normal, shearing, and bearing stresses. So let's jump to the problem. So if this is our configuration, you can easily see the concentrated load applied at the pin at B. This is the front view of our structure. Dimensions are provided like the distances, diameters, and the cross sections. And this is the front view of our geometry. And then we can also see it from the top at the rod. We see from the top view. This is what you can see from the top for rod BC. And also we can have a closer look at the connection at B from the end view of this part. This is the end view of where the concentrated load of 30 kilonewtons applied at B. So now we have like front view, top view, and also end view of some part of our structure. So first thing to do is draw a clear cut and an accurate free body diagrams for our geometry. So this is A, this is B, this is C. Like this is the 30 kilonewton applied at B. We have like AX, AY, CX, CY, and by developing the moment, summation of moment about point C, go pin C goes 0, it just says AX AX times distance, which is 600 millimeters, which is zero point 0.6 meters, minus 30 times 800 or zero point 0.8 meters goes 0. It just gives us AX is positive 40 kilonewtons, and this positive, it just says the direction of our calculation is consistent with our arbitrary direction because we just choose this arbitrary direction for CX, CY, AX, XY, AY. So it just says if this is consistent, it just says AX is a push. So that's a compressive force. Summation of force in X goes 0. It just says 2X component AX and CX. So CX is a outward, it's negative, so it's not consistent with the arbitrary direction, so that's a like outward C. This is our CX in terms of direction. So then summation of forces in Y goes 0, just gives us a AX plus CY should cancel out this 30 kilonewton, AY plus CY should cancel out the 30 kilonewton, and like if you create a moment based off about point B, it just we are canceling out CX, CY because the force of rod BC goes through the point B, so we only have like AY which is applied at here, and it just says AY is 0. If AY is 0, replace it in the previous equation, it just gives you CY is equal to 30 and AY is 0. So as soon as we have the forces, we can re rearrange the format as soon as we have the direction of AX, CX, CY. So CY is upward, CX is like outward, AX is inward. So as soon as we have them, we can just replace, create the law of sine for our structure. So we have like 30 kilonewton at B, FAB, FBC. And if we just move this force over here, so we are just replacing this 30 kilonewton over here to create our triangle for using the law of sine. As soon as we have that, we can easily, based off the dimensions like 600 millimeters, 800 millimeters. So this is 4 in horizontal direction, x direction, a 3 in rise over run, and also this is the hypotenuse. So as soon as we have this golden ratio, we can just jot down the law of sine. It just says FAB to this length is equal to FBC to 5, FBC to 5, and that's 30 to 3. So as soon as we have that, we can write it down, solve it for FAB, and it just gives us that's 40 kilonewton. Then other times solve it for FBC, and it just gives you FBC is 50 kilo. We already know the direction, so it's just the numerical value of those forces. And then if we just apply them in our boom and rod BC, it just says this is a compression and this is a tension. The compression at boom AB and tensile force or tension at rod BC. Thank you. Now we have all the forces. We can just jump to the sections for in next video. We're solving the problem for normal stresses, shearing, and bearing stresses. Thank you. See you then.